Hello there, welcome to section 11.1 where we're going to really shift gears and move away from sequences and series and move into what are known as parametric equations. And so to start things off, let's check out the first question on the worksheet, where in part A it says plot the curve C described by the parametric equations given here by completing the table and plotting points. Okay, so what we're looking at here for the presentation of this curve C is a set of ordered pairs where for every value of t in this interval, the x-coordinate of the ordered pair is 2t minus 1 and the y-coordinate is 4t squared. And so to complete this table, I'm just going to go ahead and plug in these values of t into these expressions, which will in turn give me xy ordered pairs. I can then go ahead and plot those ordered pairs as points in the xy plane, and that's a good first step in getting a feel for the shape of this curve C. Alright, so let's go ahead and carry that out. Now, the x and the y coordinates are what we refer to as the rectangular coordinates of these points. And as we mentioned, right, x and y are given by these expressions in terms of t, which in this context, t is referred to as the parameter for this set of equations. Okay, and this all together is known as a parametric representation for the curve C. All right, now when the parameter t is equal to -1, x is 2 times -1 minus 1, so that's -3, and y is 4 times -1 squared, and that's +4. So here I can then go and plot the point -3, 4, and this is just telling me that I'm at this location when the parameter t is equal to -1. All right, when t is 0, x is -1 and y is 0, so we're at this location -1, 0 when t is 0. When t is 1, we're at 1, 4, and when t is 2, we're at 3, 16. All right, so now I'm going to go ahead and draw a smooth curve through these 4 points, and notice that I've included these arrows. Okay, these arrows indicate the direction of increasing t. Okay, so you want to think about a parametric representation of a curve in a dynamic way. Think about motion of a particle along a trajectory. So here, when t is -1, the particle is located at -3, 4, and then as t increases, the particle is going to move along this path as indicated by these arrows. Okay. Now, in the context of motion, it's natural to think about the parameter t as time. Okay, but in other contexts, the parameter can represent other types of quantities, like say a geometric quantity like an angle. Okay. All right, cool. So now looking back here, right, from these points in the table, I just got, well, 4 discrete points. And you might object and say, well, how do you know that the curve doesn't do something more irregular between these points? And I think that's a fair objection. But if you look at these relationships between x, y, and t, note that x is a linear function of t and y is a quadratic function of t. And as we're going to show here in a moment in part B, that actually implies that y is a quadratic function of x. And so this, in fact, is a portion of a parabola. Okay, so looking at part B, it says plot the curve by eliminating the parameter. And what they mean by eliminate the parameter is to say, well, write an equation that relates x and y that does not make reference to this parameter t. All right, so we can do that as follows, right? X is 2t minus 1 and y is 4t squared. So I'm going to start by solving for the parameter t in the equation for x. I get that t is equal to x plus 1 all over 2. Now I'm going to substitute this expression in for t in the equation for y. And that gives us that y is 4 times the quantity x plus 1 all over 2 squared. And note that when you square the 2 down here, you're going to get a 4. And so this 4 and the 4 in the denominator are going to divide out, and so we're left with this quadratic relationship, right? Y is equal to x plus 1 quantity squared. So in fact, this curve C is a portion of a parabola. Okay, so now we refer to these equations, where here I'm including the bounds on t, as parametric equations for this curve C. Okay, now this curve here, where I'm just writing down this relationship in terms of x and y, not making reference to the parameter t, as a rectangular equation for c. Note also that I have to put bounds on x because we're just describing a portion of the parabola, okay, not all points to satisfy this relationship. All right, cool. So now for part C, it says, consider the curve C star described by the parametric equations given here. How is this curve similar to C? How is it different from C? All right, so let's go ahead and start out by just creating a table like you see above and plotting some points. And here, t varies from -4 to 2. And I'll go ahead and just take step sizes of 2. So I'll plot the corresponding points when t is -4, -2, 0, and 2. Okay, so plugging in t equals -4, get that x is 3 and y is 16. When t is -2, x is 1 and y is 4. And then when t is 0, we're at -1, 0. And when t is 2, we're at -3, 4. So note that these, of course, are the same 4 points that we see in part A, but now, right, when t is -4, we're up here, and as t increases, right, we're moving in this direction, okay? And based on our discussion in part A, right, I'm just drawing this smooth curve through these 4 points. You might say, well, wait a minute, I mean, is this actually a portion of a parabola? Is it the same portion of the same parabola that we're seeing here in part C? Well, to nail that down, let's go ahead and eliminate the parameter just like we did in part A. Okay, x is -t minus 1, and so t is -x minus 1. Substituting this expression in for t in the equation for y gives us that y is equal to -x minus 1 squared. Now note I can factor out the -1, and since I'm squaring, right, this equation is equivalent to saying that y is equal to x plus 1 quantity squared. And as we can see from this picture, x varies from -3 to 3. So in fact, this is the same curve as we saw in part A, but it's presented by different parametric equations, okay? And if I'm thinking about motion of a particle, okay, so you can think about, well, the particle is moving along the same road, okay, but it's traversing that road in a different way, right? Now we're moving in this direction as opposed to this direction. The other thing I want to say here is that these parametric equations, okay, they not only are indicating a certain direction of motion, there's also things like velocity, and so in turn speed, and things like acceleration encoded in these equations, okay? That's all stuff we'll get to down the line, okay? But I just want to point that out, that these equations have a lot of stuff packed into them. They're not simply describing the road itself. There's also a means in which they're describing how you're moving along that road, okay? So that's one of course, the benefits of working with parametric representations and why physicists and engineers really, really love this approach. All right, cool. So now what I want to do for the very last thing in this video is show you how you can plot a curve that's described parametrically on Desmos. So you can do this by just entering in ordered pairs. Okay, so I'm going to go with part A. We had 2t minus 1 and then 4t squared. And note it's asking me for bounds on t, and there we had that t varied from -1 to 2. And you see there's that portion of the parabola that we saw in part A. Now, to make this a little more dynamic, you can add in what's called the slider. So I'm just going to put in these same equations, but I'm going to use, instead of t, the letter A. And it's asked me to add a slider, so hit yes. And then here I'm going to put bounds on A, because it's really just playing the role of t. Okay, so now if I back it up here, when A is -1, we're located right there, right? Now if I hit play, right, this gives me an image of how this particle is moving along this path. And you can see, right, that the particle is not moving with constant speed, right? It appears to sort of speed up around this area. And again, we'll get to things like describing velocity, acceleration, all that in a little bit next couple sections. All right, cool. So now we'll pause that for the moment. Let's go ahead and plot what we saw in part C. So we have minus t minus 1, comma t squared. And there t varied from -4 to 2. And then I'll, like I did up above, put in a slider. Use any letter you want. Since I've already used A, I'll just use B. B squared. And then we can put the bounds on B now. And you can see, right, that the curve just perfectly overlays what we saw in part A. That makes sense. And now as far as how we're moving along the path, right, so when B is -4, we're located up here now, and when I hit play, right, I move like this along the path, and you can see it, I slow down in this region here, and then there's a speed up there. Okay. Well, great. That is a good place to stop. Good place to jump off into the next couple examples, and I will see you there. Thank you so much.